So in this topic, we're going to introduce how to solve trigonometric equations from an analytical point of view, that is using algebra and trigonometry techniques. So we're going to start with some basic concepts. For example, here, if we're asked to solve the equation 2 cosine x minus 1 equals 0, we can use some algebra to rewrite this equation. All right, so if we have 2 cosine x minus 1 equals 0, we can add 1. So 2 cosine x equals 1 and divide by 2. So cosine x is 1/2. And now from here we have to use some trigonometry concepts. Well, the cosine is 1/2. If we remember, well, where's the cosine? That's the a coordinate. If the a coordinate is 1/2, that's poorly drawn. We have two angles that we can draw over 0 to 2 pi. Alright, so we have an angle, here's one angle, and over 0 to 2 pi, here's a second angle. But they have the same reference angle. Okay, and so if we remember for the cosine to be 1/2, we remember that our reference angle is then pi over 3. And so x1, our first angle, is pi over 3. And then our second angle, x2, right, to get this rotation x2, to get all the way around to the second angle, we would have 2 pi and subtract the pi over 3. And so then that's 5 pi over 3. And we knew those, we've seen exercises like this for a while. This has been on each of our first 3 tests. I've asked you an exercise like this. So our two solutions then for this exercise are pi over 3 and 5 pi over 3. Because we were given a specific interval to look 0 to 2 pi. Now in the second part of this exercise, it just says solve 2 cosine x minus 1 equals 0. Well, again, I can rewrite this statement, just algebraically I can rewrite it as then cosine x is 1/2. And I say, well, how is that different from the previous exercise? On the previous exercise, we were only looking over the interval 0 to 2 pi. Here, we aren't given an interval. Well, it's the same basic equation. It's still saying cosine x equals 1/2. The only difference is now we don't have any specific interval. And so if we remember that the cosine function has a period of 2 pi, then we'll have our two base solutions, but they'll repeat according to the period. So then our solutions are given by the fundamental solutions, pi over 3 and 5 pi over 3. And we can add any 2 pi times k, where k is an integer. And basically what this is saying is we have our fundamental solutions, our pi over 3 and 5 pi over 3, and then any complete rotation about the circle gives us another set of solutions. So in this example, we had a specific, this 1/2, the cosine being 1/2, this was one of our nice numbers. What happens if we don't have nice numbers? Let's consider some examples. So what if we had the example 5 cosine x minus 4 equals 0, and again let's consider over 0 to 2 pi. Well, using some algebra, I can write this as cosine x is equal to 4/5. Now the problem is 4/5 is not one of my nice numbers, right? It's not a half, it's not a root 2 over 2, it's not a root 3 over 2. And so if we think, okay, well, cosine x being 4/5, that's the a coordinate is about, here, somewhere around there. And so again, I have two fundamental solutions. Here's one of them, looks like this. It's tough to draw these lines using the tools I have. Alright, so here's one solution. Let me call that x1. And a second solution over 0 to 2 pi looks like this. Here's x2. So now, again, 4/5 is not one of our special numbers, so this is not going to be one of our special angles. However, I can use the inverse trigonometric functions to help me in my solution. So, if we remember how the inverse trig functions work, we can say that x1 is the cosine inverse of 4/5. Now, x2 will have that same reference angle. x2 is 2 pi minus the cosine inverse of 4/5. So this angle right here, right, this x1, this cosine inverse of 4/5, is this angle right there in black. And so then x2 is 2 pi minus that, a full rotation, and then take away the reference. Now, of course, we can approximate these if we have a calculator handy. So using my calculator here, I have that x1 is approximately 0.644 radians. x2 is approximately 5.640. Again, those are approximations. Alright, so what I wrote in blue was exact. Cosine inverse of 4/5 is exact. 2 pi minus cosine inverse of 4/5 is exact. What I wrote in red are approximations. Now, again, if we were just solving the general statement, 5 cosine x minus 4 equals 0, again, we would have those same two solutions, but now we would be able to find more solutions by adding multiples of 2 pi. So the solution for this equation, again, without any specified interval, would be x is given by the cosine, either of the two values, cosine inverse 4/5, or 2 pi minus cosine inverse of 4/5, plus 2 pi times k, where k is again an integer. Alright, now, what if it was the second equation here? 5 cosine x plus 4 equals 0. Alright, using a little, again, over 0 to 2 pi. Again, using some algebra, we can rewrite this as cosine of x is negative 4/5. Alright, and so if we think of that on our unit circle, there's the negative 4/5 as the a coordinate. And so here's the first angle. Here's the second angle. So here's x1. And there's x2. Alright, so x1. Again, by the way the inverse cosine works, x1 is the cosine inverse of negative 4/5. And x2, again, notice that x2 has the same reference angle. Here's the reference angle, x1. Right, there's the reference angle. So then x2 is then 2 pi minus cosine inverse of negative 4/5. And again then, if we were solving the general equation, 5 cosine x plus 4 equals 0, then the solutions would be that x is those two values we stated earlier. I'll just again use the same x1 and x2 from the left, plus 2 pi times k. So that's how we would deal with the cosine function. Let's take a look at the sine function. So again, let's say 5 sine x minus 4 equals 0 over 0 to 2 pi. So then this is the same as writing sine x is equal to 4/5. Alright, so the sine x we've associated with the b coordinate. So there's the b coordinate as 4/5. Alright, so then my two angles. Here's one angle. Alright, so here's my x1. And my second angle. So there's my x2. Alright, x1 comes directly from the inverse function. x1 is the sine inverse of 4/5. Now, let's think about the x2. To get to the x2, I have the same reference angle here. There's the reference. And so I'd have to go out to pi and then take away the reference. x2 is pi minus the sine inverse of 4/5. And again, we can approximate those using the calculator if we have a calculator handy. Again, the general solution then, instead of looking over 0 to 2 pi, looking over the entire domain. So then x would equal since the sine function has a period of 2 pi as well, then we would have that x is equal to x1 or x2, right, from previous. And again, we'd have plus 2 pi times k, where k is an integer. Now, 5 sine x plus 4 equals 0. That's equivalent to writing sine x is negative 4/5. Now, this is the trickiest one, when the sign is negative. Alright, so we again sort of think about, here's where the b coordinate is negative 4/5. So then we get two angles. There's one. There's two. Now, over 0 to 2 pi, we would think, here's the first angle, there's my x1, and my second angle goes to here, there's the x2. Now the problem is, if I use the inverse function, let's think, where is the sine inverse of negative 4/5? If we remember how the sine inverse works for a negative number, that sine inverse, I'm going to put a little star next to it, that's this angle right here. The sine inverse of negative 4/5 is right there. So how do we write the x1 and the x2? The x1 is a third quadrant angle. x1, to get to x1, I would have to start at pi, right? So if we think about how to get to x1, I have to sweep to pi, and then I have to add an angle. I have to add more. But the sine inverse of negative 4/5 is a negative angle. So I'd have to start at pi, and I'd have to subtract the sine inverse of negative 4/5. Because the sine inverse of negative 4/5 is a negative angle, so I'm subtracting a negative angle, which is the same as adding a positive angle. Now for x2, I go all the way out to 2 pi, and then I have to subtract the reference. Well, the reference is already negative. So x2 is 2 pi, and add sine inverse of negative 4/5. This is the trickiest one. Since my inverse is a negative, I have to think a little differently. And that's what makes that one so difficult. That's the toughest situation, when your reference is a negative angle. Then, just like before, since the sine has a period of 2 pi, then we would have, for our general solution that x is the x1 or x2 that we stated earlier, and add 2 pi times k to give us any further rotations. All right, so that's how we deal with the sine function. What about the tangent? So the tangent isn't too bad. 5 tangent x minus 4 equals 0. So again, we use a little bit of algebra. I can rewrite this as the tangent of x is 4/5. Then I say, okay, well, where is the tangent positive? The tangent is positive in quadrants 1 and 3. So let me just draw an angle. It doesn't have to be as specific as for the sine and the cosine. I'm going to draw a quadrant 1 angle, and I'll draw the quadrant 3 angle with the same reference. So there's roughly where the tangent x is 4/5. Alright, so now here's my reference angle. There's my reference angle. There's my reference angle. Now, for the tangent function, the reference angle, so here's the x1, right? x1, there's my x1, and here's the x2. x1 is the tangent inverse of 4/5. That's how that inverse function works. That's a positively measured angle because of how the tangent inverse works. So then x2 is just pi plus tangent inverse of 4/5. And again, we can approximate those. Now, if you remember, the tangent function has a period of pi. So if we were solving this generally, we only need one solution, and then we keep adding multiples of pi. So generally, for this one, if 5 tangent x minus 4 equals 0, then x is simply the one solution we need. So I'll just say x1. That's the only, right, I only need one fundamental solution, the x1, and from that I will add pi times k. Because remember, the period of the tangent function is pi, not 2 pi. Now, this other example where I have 5 tangent x plus 4 equals 0, that's equivalent to writing that the tangent of x is negative 4/5. And so then if we were to draw, where's the tangent negative in quadrant 2 and in quadrant 4? So here's x1, and here's x2. Now the problem, though, is that if I use the inverse function, then the tangent inverse of negative 4/5, if you remember how that tangent inverse works, it's actually a negatively measured angle. So x1, one way to write x1, if we're over 0 to 2 pi, x1 would be the tangent inverse of negative 4/5 and add pi. Right? If we sweep clockwise and then add pi to get the half rotation. Similarly, x2 would be the tangent inverse of negative 4/5 plus 2 pi. Right? Sweep negatively and then add a full rotation. And then if we had the general solution, if we weren't looking over 2 pi, over 0 to 2 pi, but just over the entire domain, then x would equal the fundamental solution, tangent inverse of negative 4/5. And again, from that we could add pi, any multiple of pi, and that would give us more solutions. Alright, let's consider one more example in this part. What if we had to solve 4 sine x minus 5 equals 0? So I change the numbers around and say, well, okay, well now, this is the same as saying sine x is equal to 5/4. Now 5/4 if you remember, 5/4 is greater than 1. Isn't it? Right? 5/4 is 1.25. And so if we wanted the sine to be 1.25, where's the b coordinate 1.25? There are no places on the unit circle where the b coordinate is 1.25. This has no solutions. This has no real solutions. So you have to remember that for the sine and the cosine function, the range is -1 to 1. And so if we're trying to solve where the sine or the cosine is greater than 1 or less than -1, we can't solve those. There's no restriction like that on the tangent function. All right, so that completes the first part of this lecture.